All right, let's jump right in with this deep dive, A Brief History of Time by Stephen Hawking. And we're looking at this through the really cool oral audiobook version they've got on YouTube. I gotta say, when I started listening, I was just floored by how Hawking walks us through like the whole history of how we've thought about the universe. And I mean, starting way back, with the ancient Greeks and all the way to these crazy mind-bending ideas. It's quite a journey.
Oh, absolutely.
Yeah.
Yeah, it really shows you how our perspectives have changed so much. It's
Yeah.
like you start with Aristotle and his four elements, right? You've got earth, air, fire, and water. And
Yeah.
these were like the fundamental building blocks of the universe, at least according to him. But then you've got this other idea that pops up, the atomic theory.
Yeah.
Like it says, hold on a second. What if everything is actually made up of these tiny little particles called atoms, these things you can't even see?
It's wild how that debate, like whether things are continuous or if it's all just tiny bits stuck together, I mean, that argument, it's been going on forever in physics. Even Newton, with his whole theory of gravity, even he couldn't really make it work with this idea of a static universe. And there's this funny bit in the audiobook about how Newton just straight up dismissed the idea that the universe could be expanding. Just goes to show you that even the smartest people can get stuck in their ways.
Yeah, it's a good point. It's like a reminder that science is always changing. What might seem groundbreaking today could be totally debunked tomorrow.
You got that right. And talking about stuff that really makes you rethink everything, what about Olber's paradox? This one really blew my mind. So it basically says, if the universe is infinite and it's just sitting there static, why isn't the night sky as bright as the sun? Because, I mean, if you think about it, every single line of sight should end on a star, right?
That's the whole paradox right there.
Mm.
And it really started to poke holes in the whole static universe model. Because you see, the idea of the universe just hanging out, not changing, well, it just doesn't quite match up with what we actually see out there.
Which brings us to one of the biggest game changers in, the history of thinking about the universe, the expanding universe. This guy, Edwin Hubble, using the Doppler effect. Like when an ambulance siren goes, nee, as it comes towards you and whoom, as it goes away. Well, he used that same idea with light. And what he saw was that the light from far-off galaxies, it was redshifted. And that means those galaxies were moving away from us.
And not just moving away, but the farther away a galaxy was, the faster it was zooming away from us. It was this redshift thing that really changed everything.
Mm.
It meant the universe wasn't just sitting still. It was actually expanding, getting bigger, like blowing up a balloon. And it meant that somewhere, way back in time, everything must have started from one single point.
Talk about a light bulb moment, right? And what's even crazier? Even before Hubble had all this evidence from looking at the sky, there was this physicist, Alexander Friedman, and he had already predicted this whole expanding universe thing. He figured it out just by thinking about the universe in a really simple way, assuming that it looks pretty much the same everywhere you go and in every direction.
Friedman, he was onto something.
Yeah.
Even though people didn't really buy it at first, his work ended up giving everyone the tools to understand what Hubble was seeing. And get this. Even Einstein, Mr. Relativity himself, even he wasn't too keen on this expanding universe thing at first. He actually went and added a whole term to his equations called the cosmological constant, just to make the universe stay static.
Don't you believe it?
He later called it his biggest blunder after Hubble's discovery.
It's just amazing how all of these different pieces fit together. You've got the theories, then the actual observations from telescopes, and even some pushback from some of the biggest brains in history. And it all came together to completely change how we see the universe. And if the universe is expanding, I mean, it makes you wonder what it was like way back when, right? So enter the Big Bang, this mind-blowing idea that the universe started from this super hot, super dense state, and it's been expanding and cooling down ever since.
Yeah, the Big Bang, it's not just a scientific idea. It's something that makes you think about all sorts of things, like where do we come from? What does it all mean?
Yeah.
And, there were other theories out there trying to explain the universe. Of course, you had the steady state theory, which said that the universe didn't really have a beginning or an end, but it couldn't explain some things that we were actually seeing.
Yeah.
Well, one of the biggest nails in the coffin for the steady state theory was the discovery of this thing called the cosmic microwave background radiation. It's like this faint afterglow from the Big Bang that's all over the universe, and it basically gives us a snapshot of what the universe looked like when it was just a baby, like just a few 100,000 years old.
And the story of how they found that cosmic radiation, it's pretty wild, right? These two guys, Arno Penzias and Robert Wilson, they were just trying to build a better microwave antenna. And they kept picking up this annoying hiss no matter where they pointed the antenna. They even thought it was bird poop messing up their equipment.
I know, right? But they checked everything, and finally they realized what it was. This faint echo of the Big Bang, this radiation coming from the very early universe. Talk about stumbling onto a major discovery.
It's amazing how something that seemed like a nuisance actually turned out to be one of the biggest pieces of evidence for the Big Bang. It's like we're listening in on the universe's baby cries, right? So we've got the universe starting with a bang, it's expanding, and it's full of this faint radiation. But let's switch gears a little and talk about something else that's pretty mind-blowing. Black holes. Hawking actually traces the idea of black holes all the way back to 1783 when this guy, John Michell, came up with this idea of dark stars. These were stars that were so dense that light couldn't even escape from them.
It's kind of crazy how they were thinking about these things even before Einstein came along and gave us general relativity.
Right.
It was Einstein's theory that really helped us understand how black holes work. Basically, when a giant star dies and collapses, it can get so dense that it warps space and time around it so much that nothing, not even light, can escape.
And then there's the event horizon, right? Like the point of no return. If you cross that line, you're not coming back. It's like falling off a cosmic waterfall. And we actually have proof that black holes exist too. Things like quasars. These things are super bright, and we think they're powered by supermassive black holes that are gobbling up stuff in the centers of galaxies.
Quasars, they're like the ultimate cosmic light shows, and they're powered by these incredibly powerful black holes sucking in matter and spewing out energy. It's just further proof that these crazy objects really do exist.
But here's where things get really wild. Hawking's own research showed that black holes, well, they're not actually completely black.
Right, that's Hawking's big contribution. He found out that black holes actually give off a tiny bit of radiation because of some quantum effects happening near the event horizon. This Hawking radiation, it's super faint, almost impossible to detect, but it has some really big implications for how we understand black holes and even information itself.
Okay, so we've gone pretty deep on these big objects like stars and those crazy black holes. But Hawking, he doesn't stop there. He takes us even further down the rabbit hole into the world of the super tiny, the quantum realm. It's like switching from a telescope to a super powerful microscope, right?
It really is. And this shift in how we're looking at things, it's just as mind-blowing as when we realized the universe wasn't static. You see, before all this quantum stuff came along, physicists, they thought the universe was pretty much like a clockwork machine.
Yeah.
Everything was predictable. You know, like if you knew where everything was and how it was moving at one point in time, you can theoretically predict the whole future.
Yeah, like a giant cosmic pool table, right? You hit the ball just right, you know exactly where it's going to go. But then quantum mechanics, it throws a wrench in that whole idea. It says, nope, there's actually a lot of uncertainty baked into reality. Like when I first read about Heisenberg's uncertainty principle, I was like, wait, so you're saying we can't actually know everything for sure?
That's the gist of it, the uncertainty principle. It basically says that you can't know both the position and the momentum of a particle with perfect accuracy. The more you nail down one, the fuzzier the other one gets. And it's not because our instruments aren't good enough. It's a fundamental rule of the universe.
So it's not just that our measurements are a little off. There's like this inherent blurriness to reality.
That's right. And this blurriness, it's not just some abstract idea. It has real consequences, like take wave-particle duality. Hawking talks about how particles, like electrons, they can act like both waves and particles at the same time. Super weird.
It's like saying, hey, sometimes this baseball is actually a ripple in a pond. And then there's that double slit experiment. That one still makes my head spin. You shoot a single electron at a barrier with two slits in it, and it somehow goes through both slits at the same time.
Yeah, that experiment, it's a classic example of how strained quantum mechanics is.
Yeah.
Instead of following a straight path, like you'd expect, the electron is in this weird state of being in multiple places at once. Until we try to measure it, that is...
So it's like the act of observing, of measuring, that forces the universe to choose one outcome from all the possibilities. Makes you wonder what's really going on down there. And it's not just particles that act this way, right? Hawking explains how energy also comes in these little packets called quanta.
It's like you can't have half a photon of light, you know? It's either a whole photon or no photon at all. It's like the universe has these fundamental Lego blocks, and everything is built from those blocks.
And this whole quanta thing, it totally changes how we think about atoms. Explains why atoms emit and absorb light at specific frequencies. It's what gives them their own unique fingerprints.
Right. It's a totally different picture from those old models, where electrons were just like tiny planets orbiting the nucleus. The quantum model, with its discrete energy levels, it's a revolution in how we understand matter.
Okay, so we've gone from a universe that seemed predictable to one that's full of uncertainty and probabilities. But how does all this quantum weirdness fit in with the big picture? I mean, we've got general relativity explaining gravity and the large-scale universe, and we've got quantum mechanics describing the world of the super small. How do we get those two to play nice?
Ah, that's the big question, isn't it? Finding a way to combine general relativity and quantum mechanics to create a theory of quantum gravity. That's been the holy grail for physicists for a long time.
It's like we need a whole new language, a new set of rules to describe a universe where gravity and quantum mechanics can coexist.
Exactly. And Hawking, he dives into some of the leading contenders in this search for a unified theory. One of them is supergravity.
Supergravity sounds like something out of a comic book.
It might sound like that, but it's a serious attempt to bring all the fundamental forces together.
It introduces this idea called supersymmetry, which basically says that every known particle has a partner particle, a superpartner. So like for every electron, there's a selectron, and every quark has a squark. Do they hang out in supersecret layers too?
Well, we haven't found their secret layers yet, or any evidence of these superpartners for that matter. That's one of the big challenges with supergravity. These particles, if they exist, are really massive and hard to find with our current technology.
So it's a waiting game, huh? We need bigger, better experiments to really test these ideas. But Hawking doesn't stop at supergravity. He also takes us through string theory, which is even wilder.
Yeah, string theory. It says that the universe isn't made of point-like particles, but tiny vibrating strings, like little strands of energy. And the different ways these strings vibrate, that's what gives us all the different particles and forces we see.
It's a really elegant idea, right? The universe as a giant cosmic symphony. But I've also heard that string theory needs more dimensions than the three we're used to.
Yeah, that's one of the things about string theory. For the math to work out, you need extra spatial dimensions, curled up into tiny spaces so small we can't even see them.
So it's like we're living on this three-dimensional sheet, but there's a whole bunch of other dimensions all around us that we're just not aware of. That's pretty trippy. But does string theory actually make any predictions that we can test? Or is it just a really cool mathematical idea?
That's a big debate in the physics world. It's a super complex theory, and it hasn't yet given us any clear-cut predictions that we can easily test. But people are working on it, and who knows, maybe one day we'll be able to see the effects of these tiny strings.
So for now, string theory remains this tantalizing possibility, a potential key to unlocking the deepest secrets of the universe. But even if we did find this theory of everything, this equation that explains all the forces and particles, there are still some really big questions that science might not be able to answer. Questions about why the universe exists, what it all means.
That's where Hawking takes us next. From the mind-bogglingly small to the biggest questions of all. The nature of time, the origin of the universe, and the meaning of existence.
Man, we've covered some serious ground, haven't we? From the vastness of space to the weirdness of quantum mechanics. And now we're tackling something that feels like, well, it's just part of life, time. But when you really stop and think about it, what even is time? I mean, we experience it every second, but can you actually explain it?
It's one of those things that's had philosophers and scientists scratching their heads for centuries. Hawking takes us through all these different ideas about time. Like before Einstein, everyone thought time was this absolute thing, ticking away at the same rate for everyone, no matter what. But relativity threw a wrench in that. It showed that time is all tangled up with space, and it can be warped by gravity and how fast you're moving.
Right. So if you're zooming around near a black hole, time slows down for you compared to someone who's just chilling on Earth. It's like something straight out of Star Trek.
But even with relativity, there's still this thing, Time seems to move forward, from past to present to future. Hawking calls this the arrow of time. And one thing that really got me thinking was why time seems to have this direction when the laws of physics themselves don't really care about which way time goes. Like, why can't we remember the future?
That's the big mystery of the arrow of time. If you take the equations of physics and run them backwards, they still work perfectly. So why do we only experience time moving in one direction? Well, Hawking connects this arrow of time to something called entropy.
Entropy, right? I remember that from high school physics. It's like a measure of how messy or random things are, right? Kind of like my desk. No matter how much I try to keep it clean, it always ends up cluttered. Is Hawking saying that there's a link between how messy the universe is and the direction of time? You got it. The second law of thermodynamics says that entropy always increases over time, at least in a closed system. So things tend to go from order to disorder. Like think about dropping a glass. It shatters into a bunch of pieces, but you never see those pieces spontaneously jump back together and form a whole glass again. Hawking suggests that this increase in entropy is what gives us the feeling of time moving forward. So the Big Bang, this super-ordered, low-entropy state, that's the beginning of time as we know it. And as the universe expands and stuff happens, entropy goes up, and we get this sense of time marching on.
So it's like the universe is this big cosmic clock that's slowly winding down, heading towards this state of maximum messiness. Kind of a depressing thought, isn't it?
It can seem that way. But Hawking also brings up this crazy idea of imaginary time, where time is treated like another dimension of space. That one took a few listens for me to even begin to wrap my head around.
Yeah, imaginary time. It's tough to picture. Hawking uses the analogy of the surface of the Earth. The Earth's surface, it doesn't really have a beginning or an end. You can just keep walking in any direction. So imaginary time, it's kind of like that. It could allow for a universe that doesn't have boundaries in time, a universe without a beginning or an end.
Exactly. With imaginary time, you don't need a Big Bang singularity, no moment of creation. The universe just exists eternally in this imaginary time realm.
So it's like with imaginary time, the Big Bang never even happened. The universe just always
In
was.
a way, yeah. And Hawking suggests that both descriptions, a universe with a Big Bang in real time and a universe without boundaries in imaginary time, they could both be valid ways of looking at the same thing, kind of like looking at a sculpture from different angles. Each view gives you a different perspective.
It's mind-blowing how these ideas, they really challenge how we think about reality. And Hawking, he doesn't shy away from the big philosophical questions either. Like, if the universe didn't have a beginning, does that mean there's no need for a creator?
Hawking, he doesn't claim to have all the answers, but he does encourage us to really think about these questions. He suggests that a universe that follows the laws of physics, well, it might not need a creator in the traditional sense.
So even if we find this theory of everything, this ultimate explanation for the universe, there will always be questions that science can't answer, right? Questions about why we're here, what it all means. It's kind of humbling to realize that even with all our scientific progress, there are still mysteries that we may never solve.
That's the beauty of it, I think. This whole journey through a brief history of time, especially with this awesome audiobook version, it's been more than just learning about science. It's been about curiosity, about wondering about the big questions. It reminds us that there's always more to learn, always more to explore.
Absolutely. This deep dive has been a wild ride. We've talked about the Big Bang, black holes, the weirdness of quantum mechanics, and even pondered the very nature of time. And you know what really struck me? It's that sense of awe and wonder that Hawking brings to it all.
It's like he's reminding us that we're part of something much bigger than ourselves, and that there's so much out there that we still don't understand.
So, to everyone listening, keep those questions coming. Keep exploring. Keep diving deeper into the mysteries of the universe. And until next time, keep those brains buzzing.